Okay, so today we're going to be talking about isotopes. Now, we know that isotopes are a group of atoms of the same elements that varies in mass and the number of neutrons. Okay, this pretty much means I can have a whole bunch of hydrogens, and each of those hydrogens have a different atomic mass. Because each of those hydrogens have a different atomic mass, all of those hydrogens are considered isotopes. Now, the reason why isotopes have a different number of neutrons to one another is because we know that the atomic mass equals the number of protons plus the number of neutrons. So the reason why we say it's a different number of neutrons, why are we saying that isotopes isn't changing the numbers of protons? Well, we know that the atomic number equals a number of protons. If we change the protons, we're changing we're changing the element itself because it's changing the atomic number. And each element has their own significant, unique atomic number. So that's why isotopes have different number of neutrons. Now there are two notations for representing an isotope. The first one is atomic name dash and its mass. So let's say I have hydrogen that has a mass of 2. I would want to label that hydrogen dash 2. Or let's say I have carbon with a mass of 12. I would say carbon dash 12. The other way of notation is we have an X here with the superscript of A and a subscript of Z. Now, the X is the atomic symbol for the element. We know that the atomic symbol for hydrogen is capital H, so X would be capital H. The atomic symbol for sodium is capital N, lowercase a, so X would be capital N, lowercase a. The A represents atomic number, so whatever atomic number that specific element has. And then Z represents the atomic mass, the mass of the element, in that whatever that element's mass is. Now, the atomic mass on the periodic table is the average atomic mass of the elements. So we all see if you look at a periodic table, all of the elements' atomic masses are have decimal places. And yesterday, when we were trying to find the number of neutrons, we wanted to round the masses to the whole number. Well, why are the atomic masses just in whole numbers anyways? The atomic masses that we see on the periodic table is the average atomic masses of all of the isotopes that specific element has. Now again, yeah, it's all the average of the isotopes' masses. And that is how you usually calculate them. So we have isotope 1 mass, so whatever mass that first isotope has, multiply the abundance percent. So the scientist will find, well, what's the percentage of that isotope present in nature? But we convert that percentage to a decimal, then we'll add the isotope 2 mass times that abundance percent in decimals. So let's go ahead and practice those calculations. Okay, so let's do an example of these types of calculations. So example number 1, we got rubidium 85 with a 72.2% abundance, and rubidium 87 with a 27.8% abundance, okay? Now the first steps we always want to do, since we need to use the decimal percent of the abundance, is to convert these two percentages to decimal numbers, okay? So all you do to transfer a percentage into decimal numbers is you're going to move the decimal point twice to the left. Move it twice to the left, okay? So 72.2%, moving the decimal twice to the left, you're going to get 0.725.
2. Okay? And then we have 27.8%, moving the decimal place twice to the left. You're going to get 0.278. Okay? Our next step is we're going to start writing out the equation, the calculation sequence. So, we have the mass number of 85. Remember, this is going to be the notation for the isotope. We have an isotope of rubidium, the element's rubidium, and the atomic mass is 85 for that isotope. So we're going to do 85, and we're going to multiply that to the decimal number of the percentage. So what we just did, timesing the 0.722. And then we got to add the other isotopes. This is isotope 1. The other isotope, which is rubidium-87, with the 0.278 decimal abundance. So we have to multiply the 87, the atomic mass of that isotope, times that decimal abundance, which is 0.278. Now, if we had more rubidium isotopes, we'll just add and do the next one, add and do the next one, continue on. But since we only have 2, we only need to do 2 of these. Go ahead and plug that into your calculator. And then what you're going to get once you plug it into your calculator is 85.556. And again, in chemistry, all your numbers, your answer numbers need to have a unit. If you don't give me a unit, you're not going to get points. So the unit for atomic masses, whenever we find them, average atomic masses, is going to be AMU. Okay? So the average atomic mass, you'll find for rubidium on the periodic table is 85.556 AMU. And looking onto the periodic table that I have up there, it's about 85.4878, and that's very close to what we just found here. Right? Okay, so let's go ahead and do another example. So for this example number 2, we got uranium-234, which has a 0.01% abundance. Uranium-235, that has a 0.71% abundance. And then we got uranium-238 with a 99.28% abundance. And we got to find that at average atomic mass. Remember, very first step is we have to convert these percentages to decimal numbers. And the way we do that is we move the decimal place 2 times, twice to the left. We want to make the number even smaller. So again, moving the decimal place 2 times, so twice to the left. So let's go ahead and do that. For 0.01%, we're going to move it twice to the left. So we're going to get 0.0001. Very, very, very small. Now 0.71%, twice to the left. And you're going to get 0.0071, again, very small. Then we're going to 99.28%, moving twice to the left. We get 0.9928. Then our next step is we go ahead and multiply those abundance decimal numbers to its masses and add them all together. So our first isotope, we got uranium-234. That's the notation for that isotope. So our atomic mass is 234. So we take 234. And we got to multiply that number to that decimal number percent. So we'll multiply that by 0.001. Again, adding, we got to add all them together. Then we got uranium 235, so we take that atomic mass of 235.
It's 0.0001. With the answer to this problem, I did make sure that that answer represents if we had the 0.0001. That's just written wrong on the board.
And then we go ahead and multiply that by the abundance percent. And then we do it again for our next isotope that has a mass of 238. And we multiply that by that decimal percent. And then all you do is plug that into your calculator. And when you do that, you are going to get 238.1889 ANU. Remember, don't forget that unit, ANU. Okay, so let's do one more example of this. Now for example number 3, we have chlorine 35 that has a 75.53% abundance, and then chlorine 37, which has a 24.47% abundance. And we gotta find chlorine's average atomic mass, okay? Again, the very first step we gotta do is to convert these percentages to decimal numbers. And we do that by moving the decimal twice to the left, okay? Now, so let's go ahead and do that for 75.53%. And that percentage becomes 0.7553. Let's do it again for the 24.47%. And we get 0.2447. And then your next step is just go ahead and write that calculation, multiplying that atomic mass from the notation of the isotope to that decimal number and then adding them all together. So our first isotope, we got chlorine 35. That notation tells me this chlorine has an atomic mass of 35. So we'll do 35. Again, we got to multiply by that decimal number abundance that we just got, which is 0.7553. And remember, we got to add them all together. So adding, then chlorine 37, this notation tells me this isotope has a mass of 37. And we go ahead and multiply by that decimal abundance, which is 0.2447. Then you go ahead and plug that in.
The percentage goes here. The parentheses goes before the 37, not before the 0.2447. My bad.
Into your calculator, and you are going to get 35.4894 AM. And that's it.
Okay, so why don't you go ahead and do this example on your own. All right, here's the answer, 67.248 AMU. And that's it.